Let's take a look here at the last example in 3.7, and our last example of all of Chapter 3, and probably the greatest example of all of Chapter 3, Gabriel's horn. Gabriel's horn is a solid that is obtained by rotating the region R, given here, about the x-axis, and our goal is going to be to find whether or not the surface area of Gabriel's horn is finite. All right, I'm going to go ahead and try to draw out a couple pictures here to illustrate again what's going on. So again, I have my region where x always has to be greater than or equal to 1. Notice again that my y value is always going to be from 0 to 1 over x. So at x as being a 1, my y value goes from 0 to 1, and all of these points are a part of the region. As my x value continues to get larger, notice that the upper value of y, of what it can be, is going to continually get smaller. So I'm going to have something that looks like this. And this is following the curve of 1 over x. So this here is the region that I'm actually working with. And we're going to take that region and do something very surprising with it. We're going to take that region, which is infinitely long, and revolve it around the x-axis, like we did back in the first chapter. Now I'm going to draw a picture of what this would look like. So I'm going to have kind of my curve. I'm going to draw a duplicate curve on the other side, and then I'm going to play connect the dots. So I'm going to connect this, dashed line going back into the page, and I'm painting the outside because I'm interested in the surface area. So I have all of this. You might be able to see why this is referred to as Gabriel's horn, because it almost kind of looks like one of those like medieval trumpets or something like that, right? So I'm curious about what this surface area is. Well, I could first go back and think about how I calculated surface area back in the first chapter. So we know that to find surface area, right, we typically integrated from a to b. We had a 2 pi times our function, and then we had this arc length piece, which was 1 plus the derivative of our function squared, dx. But we had to meet some conditions, right? We had to be working with a function that was non-negative, and we also had to have a function with a continuous first derivative on the given interval. Well, here, we're working with an interval from 1 to infinity, but we can still definitely say that f of x is most certainly non-negative on the interval from 1 to infinity, and we can say that f prime of x, which is negative 1 over x squared, is absolutely going to be continuous on 1 to infinity. It would only be not continuous or discontinuous at 0, which isn't a part of our interval. So we would expect then to say that our surface area here would be integrating from 1 to infinity of 2 pi multiplied by our function times the square root of 1 plus a negative 1 over x squared all squared dx. Well, we can try to go ahead and see if we can try to evaluate this. It might be a little bit tricky. Okay, I'm going to go ahead and do a couple things with this. First off, I'm going to take the 2 pi and just pull it outside the integral. I'm going to have my 1 to infinity, a 1 over x, and I'm going to simplify the inside of the radical. I have a 1 plus 1 over x to the 4th dx. All right, so that's pretty good. Once I have this, I can go ahead and start to think about other ways I might be able to evaluate this integral. Notice that I can kind of think a couple steps ahead. Like once I put in my limit and I start crunching this out, I'm going to need to have like some antiderivative of this function in here? Oh gosh, this can get really messy. In fact, you could try for a long time and maybe not come up with a good technique for how to evaluate this. But here's going to be my suggestion for how to proceed. I'm going to go ahead and rewrite this integral again by simplifying what's under the radical. I'm going to get a common denominator and push the two items on the inside together. So I can write x to the 4th over x to the 4th, and then add the two fractions together. I'll get something like this. Now I can simplify this down a little bit, because that's going to turn into a 1 over x multiplied 2, and I can square root the top of the fraction and the bottom of the fraction. If I square root the bottom of the fraction, though, notice that'll just turn into x squared. And then I could simplify this down one more time by just having this as square root of x to the fourth plus 1 over x to the third. Now, this is still going to be a little bit difficult to work with. I can't really do any sort of u substitution or integration by parts or things like that to really help me very easily here. But this is again where the comparison theorem shows up and is very, very nice. Now in the last video, when we used the comparison theorem, we were just started with the idea that x was a number from 1 to infinity, and we kind of did some strange manipulations with that inequality. In this video, I'm going to go ahead and highlight a couple things that I can do when trying to use the comparison theorem. Oftentimes, what I'm going to be able to do is to think about taking my function here and thinking about ways that I might be able to manipulate it or change it. I have two goals in mind. However I change this function can be done in three different ways. I might be able to add something to the function that wasn't there before. I can remove something from the function, maybe like remove the square root or remove a power. Or I can change something. That is, like maybe I can change that power of 3 down there to a power of 7. But as I make these changes, what I'm attempting to do is to create a red or a blue function to be used with my function in the comparison theorem. Now the changes that I make, I'd like to be small. That is, I don't want to change a lot of things at once. I don't want to like get rid of a square root, get rid of a 1, get rid of a power. It's like too many things at once. Because whatever change I make, like let's suppose I make a change like getting rid of the square root symbol. That's a simple change. But two things need to be able to follow from that. Once I've made the change, I need to be able to determine which one of these items is larger. Because if I can't determine that, then I can't use comparison theorem easily. I also want to make sure that whatever my new function is, that I believe it would be easy to integrate. Now over here, notice that I might actually be able to, with the removal of my square root, actually have all of those things. Notice, would it be bigger to square root a value or not square root a value? Well, since this value is clearly bigger than 1, I can say that not square rooting it would produce a larger result. I could also see that over here, if I split my fraction, I would get x plus 1 over x cubed, which is actually very easy to integrate. So in terms of the comparison theorem, I've generated a blue function that's big, and my function's red, which means I might be able to show that if this blue integral is convergent, my smaller integral would also be convergent. But there's no guarantee of that. In fact, take a look here. This would be an example of how you can fail when using the comparison test. Notice if I started to investigate this function here, and I turned this into a limit, and I'm going to skip a bunch of steps here. Just going to jump right into the evaluation, finding my antiderivative. Let's see, this would be negative, negative 1 over 2x squared. I think that would work. And then I could evaluate this from 1 to t. If I was to simplify this all the way down, what I'm going to actually find, and you could double check me on this, is that I'm going to get something that's infinite here. That would mean that my blue integral is infinite in size. And if I go back to that comparison theorem, if the bigger function has an infinite amount of area, what does the smaller function have? I don't really know. This is going to be something that you're going to experience a lot when trying to practice with the comparison theorem. You might come across a lot of attempted changes, attempted integrals that ultimately lead you to a not helpful result. So I have to just be willing to make mistakes here. I made a great change. I eliminated a square root. I was able to determine where direction my inequality faced, and I got something that was easy to integrate. However, I didn't get a useful result. this means that I'm going to have to erase all of this hard work and try another manipulation. Let's see. How about I try something else that could result in something simple? What if I just get rid of the 1? Well, I have to redetermine the size now. Notice that both these fractions have the same numerator, same denominator, but their numerators are now different. The one on the left has a bigger numerator, which means it should be the bigger overall fraction. So notice here I've kind of swapped to make this my blue item and this my red item in the comparison theorem. Of course, I still want to make sure that what I have over here is easy to integrate. But since that's going to turn into x squared over x cubed, which is 1 over x, that seems pretty straightforward. Well, let's see what's going to happen. I'll say we see that an integral from 1 to infinity of 1 over x dx is equal to a limit as t approaches infinity of 1 to t, 1 over x dx. That's equal to a limit as t approaches infinity. And let's see, antiderivative here is going to be what? Natural log of the absolute value of t, or absolute value of x. I'm just going to go ahead and replace immediately my bounds in for that value of x, and I end up with this. Now, natural log of 1 I know turns into 0, and this, natural log of t, as t goes towards infinity, is infinite. So since the integral from 1 to infinity of 1 over x is divergent, and it's the smaller function, then by the comparison theorem, my integral from 1 to infinity of the square root of x to the 4th plus 1 over x cubed is also divergent, and thus my surface area, which is 2 pi times that integral, is divergent. So the surface area of Gabriel's horn, after all of that, is divergent. Is the surface area finite? No, it is not. And why in the world is this the greatest example in all of Chapter 3? It's a lot of work just to get something that almost seems intuitively obvious. I mean, this thing does stretch forever out towards the right, so it's not surprising that there might be an infinite surface area. But here's where it gets awesome. Can you quickly see if you could find the volume of Gabriel's horn? Go back, take a look at it. You might be able to see here your cross sections are going to be disks. Take a moment, pause the video, see if you could set up an improper integral that would represent the volume, and see if you can compute it. When you unpause, you'll see me working through the answer. Okay, so what I got is an integral that goes from 1 to infinity. I'm adding up these cross sections, which are cylinders with a little bit of thickness. So I'm going to need a pi r squared dx. Notice that the radius up here of one of these circles is going to be going from my x-axis up to the function. So I'm actually going to have a radius here of 1 over x. If I simplify this down, so limit as t goes to infinity, integral from 1 to t of pi 1 over x squared dx. This is a limit. T goes to infinity. I'm going to have a negative pi over x. Evaluated from 1 to t. This is going to look like a limit as t approaches infinity of negative pi over t minus negative pi over 1, which has a limit of pi. That means that the volume of Gabriel's horn is convergent. Okay, now you need to pause for a moment and collect your brain because it probably just exploded. I mean, this is crazy here. Think about what we've said. The surface area is infinite, but the volume is finite. Okay, how does that work? This idea of Gabriel's horn is sometimes described as like the infinite paint can. And you can kind of see this paint can analogy really highlighting just how crazy this result is. You can think of Gabriel's horn as a paint can that can't hold enough paint to paint its own exterior. Right? There's only pi cubic units of paint you could stuff into the thing, but you need an infinite amount of paint just to paint the outside shell. And here's where it gets even nuttier. If you were to imagine this thing filled with paint, right, like pi cubic units of paint, wasn't there enough paint to paint the whole inside? Like, wouldn't you be able to imagine the paint coating the entire inside of the solid? And that's easily done without even using most of the paint. Yet the outside requires an infinite amount. This is a crazy, crazy example, and it's so fun. And it really highlights why using the comparison theorem can be a really powerful tool, again, when getting to these really complicated integrals. Hopefully you found this a fun and interesting example. And if you have any questions on it, by all means, please let me know.